Structure and isomerization of coordination compounds. Isomers are substances that have the same chemical formula, but they have different structures. So the same atoms, but they're put together differently. And there are two broad categories. There are structural isomers and stereoisomers, and then there are subcategories of those. So structural isomer, the atoms are connected in different ways. So you might have this chlorine on a carbon, and on the other one it's on an oxygen or something. They're just very different. In a stereoisomer, the connections are the same, but they're arranged differently spatially. With the structural isomers, we can have coordination isomers where the ligand and the counterion exchange places, or we can have linkage isomers where the ligand coordinates to the metal by a different atom. Stereoisomers, we have geometric isomers, different arrangements around the metal ion, and we'll talk about those. And then optical isomers, which is kind of a nice lead-in to organic chemistry, the concept of chirality, handedness, right? Well, let's see where this goes. So here's an example of a coordination isomer. So this first one has chloride as the counter ion, and bromide is one of the ligands. So bromide is attached to the the cobalt, via a covalent bond, and the chloride is just floating around balancing the charge. Over here, the chloride is the ligand and the bromide is the counter ion. That makes sense? So when we're writing formulas for coordination compounds, we always put brackets around the complex ion because it's often not obvious where it ends, right? In a linkage isomer, this can happen with only a few ligands, but some of them can coordinate in different orientations. So the nitrite ion, this would probably be a good place for a Lewis structure. So the nitrogen has a lone pair that can make a coordinate covalent bond with the atom. But the oxygen over here is also available to make a coordinate covalent bond. So if it bonds on the nitrogen atom, it's called nitro. If it bonds on the oxygen atom, it's called nitrito, because they have to have different names, right? And again, we don't have to memorize these things because the exam is a take-home exam, right? We just need to be aware that these things exist so that we can look them up, right? So the name changes a little bit, but that's the linkage isomer. They're linked on a different atom.
Would the N or the O be negative?
The O would be negative. Yeah, because if you do formal charges, it's kind of messy over here, but if you do formal charges, this oxygen has a formal charge of -1. And so we would indicate that over here. So these are linkage isomers. Pentaamine nitro cobalt 3, pentaamine nitrito cobalt 3. One is yellow-orange and one is red-orange. So the color difference is not dramatic, like black and white, but there's a distinct difference in color because of how this nitrite ion is connected. Here it's connected with the nitrogen, and here it's connected with the oxygen. This is the short list of ligands that can do this. So we just talked about the nitrite ion. The cyanide ion, if you connect on the carbon, it's cyano. If you connect on the nitrogen, it's isocyano. This is cyanate, so we can have cyanato or isocyanato. And then there's thiocyanate, thiocyanato or isothiocyanado. And it's like, I don't know, it sounds like you're saying goodbye. Geometric isomers happen when those ligands have a different arrangement in space. Okay, and not all coordination compounds can have these isomers. If you have a square planar complex, here we've got platinum with 2 amine groups and 2 chloro groups. We can have these amine groups next to each other, or they can be across the metal atom from each other. Okay, and that's not the same thing. They can't just wiggle around and move. They're connected that way, and they would have to disconnect and reconnect to make the other. So this one is called trans because it's across, like the Trans-American Railroad, right? Goes across the United States. And this one is cis, cis meaning like next to, I guess. Yeah, same side. Trans is opposite sides. So this can happen when you have this general formula where you've got the metal ion and you've got 2 of one ligand and 2 of the other ligand. If you've got 3 in one, doesn't happen. All 4 the same, obviously doesn't happen. You can't just look at the formula though, because not all compounds with 4 ligands are square planar. Some of them are tetrahedral. This can also happen in octahedral complexes, where you've got 4 of one ligand and 2 of another. So here's the cobalt, and we'll look at the chlorides because there's fewer of them. So here they are next to each other, and here they are across from each other. And so this is the trans isomer, and that is the cis isomer. Any questions? And we use cis and trans here the same way as they do in OCHEM. Then there's Fastmer isomerization, or isomerism. And honestly, I'm not exactly I'm not sure how you're supposed to pronounce that. It's a facial isomer, so maybe it's facemer. What do you guys think? What should we call it? Facemer? We'll call it facemer. So facemer isomerism. So this happens in octahedral complexes where you've got 3 of each. So it's easiest to look at the chlorines here. So here, the 3 chlorines form a triangle. That's going to be one face of the octahedron. So, these would be the faces, right? And then there's one back here. So these 3 make one of the faces. So that's the face isomer. And then the other one is called mer because these 3 are like the meridian going around the middle. Okay? So the 3 ligands form an arc around the middle, or they can form a face. So face or mer. Any questions? So draw the structures and label the type of all the isomers of each complex ion. So here we have chromium, and we have 3 water molecules and 3 chloride ions. And it's probably easiest to draw the ligands just as a ball and just kind of identify them by letters or colors or something. So I'm going to make the water blue. Well, maybe not that blue. I wanted this. I wanted the highlighter. I'm going to make the water blue because water's blue. And I'm going to make chlorine green because chlorine gas is green. How's that? So we have 6 ligands. The only possible way to put them is in an octahedron. So we've got our cobalt here in the middle. And then we're going to have top and bottom. And then we've got 4 around the middle. Oops, that's not very good. I'm trying not to get into the space for the other one there. The first the first isomer is easier because you can just put them wherever. Yes?
I'm sorry, where'd you get the cobalt from?
That's an excellent question.
Transmutation?
I just, pulled it out of thin air, which I've had a lot of thin air recently. Come on, let's pick the erase. Yeah, it probably came from down there. I just moved up the page. Always happens. No, it doesn't. Okay, so I have 3 water. So I'm going to put one here, and one here, and one here. And then I've got chlorines, so I'll fill in the other spaces. And, you have to use a little visualization here. So then the other one, the basic structure is the same. But now we need to be a little more careful where we put them. So, which kind of an isomer is this one? That's the face isomer, because these 3 are in the same face, and these other 3 are in the same face. So then what I'm trying to do here is to draw the meridian, right? So let's try putting the chlorines like that. So this is a meridian, an arc around the metal ion. And then the water molecules are out here. When there's 3 and 3, now they're both forming meridians. Right? So we're supposed to label the type. So this was the face, and this is the mer. Any questions?
Does the structure ever go into like the name of it?
Pardon me?
Does the structure ever go into like the name of it?
The name of the isomer is sometimes included in the name.
I know
Yeah.
like cis and trans are.
Yeah. So these can be included as well.
Okay.
It depends on whether you care and also whether, sometimes the thing you have is a mixture of both. And so then you don't label it either one. But if you have separated them and you know you have just one isomer, then you would label it face or mer. So this one has how many ligands? What does OX mean? OX means oxalate. It has 5 ligands, but Oxalate is a bidentate ligand, which means it grabs on with both hands. So it occupies two spaces. So this is also going to be octahedral. So there's my cobalt that escaped the first time. Let's see. Chlorine's green. Make oxalate purple. I don't know why. And I'll make ammonia red, orange. So I'm going to put the oxalate on there first because it's the trickiest. So it's going to occupy two sites, and they have to be next to each other. It can't spread from this side all the way over that side. They need to be adjacent. So the ox is going to take up two of these. And then we've got two ammonias, so maybe put those there. I forgot what color I was looking for. And two of the chlorines. So let's see if we can draw another isomer. And what we want to do when we're, exploring possible isomers is we want to keep things as similar as possible. Instead of this one being like completely turned around, because it's hard to turn them around in your mind to compare them. So I'm just going to change one thing. So I'm going to switch an orange one for a green one. So I took these two and swapped them. You see that? Are those different isomers, or could you take one of them and rotate it around in space and make it be the other one? They're different, right? Here we have the chlorines across from each other, right? And here they are next to each other. So what kind of an isomer is this one? Cis. And the other one? Trans. Any questions? Bless you. Doing homework problems or working on the take-home exam, a model kit is super helpful, but you can also do it with like gumdrops and toothpicks or marshmallows and toothpicks. But sometimes it just really helps to have things that you can look at, right? And it's a good excuse to get candy and then be ashamed to throw it away, so you have to eat it afterwards. It'd be wasteful otherwise. So optical isomers. Optical isomers are non-superimposable mirror images of each other, like your two hands. My two hands are very similar. Put this one up against a mirror and it just looks like this one, right? But I can't superimpose them. If you've ever worn gloves, except, these are different kinds of gloves we have here, but like, regular, real gloves. There's a right-hand one and a left-hand one. And if you put your hand in the wrong one, it just doesn't fit very well, right? Because your thumb is not your pinky. So they are the same, but they're different. So these molecules are called chiral. The different isomers are said to be enantiomers, and they exhibit optical activity. Yeah.
Would this only really happen with like three-dimensional molecular shapes and not like planar?
Yeah, it's not going to happen with planar shapes. The one that it happens with a lot in organic chemistry is with carbon at the center in the tetrahedron. So in a tetrahedron, if you have 4 different things attached to it, it will be chiral. You'll have a left-hand version and a right-hand version. Here, this is a little different because we have, what are these? It says it's an N. We have bidentate ligands, that's what we have. So we have bidentate, So 1 ligand, 2 ligands, 3. If we look at the mirror image of this, I think we need models for this.